Today, I'm going to be talking about how DO-178C relates to timing analysis. So, in keeping with the tradition we've kind of built up over this webinar series, here's a fun little graphic to get us thinking a bit. So, we're seeing a little video game on screen, and you've got a choice. Are you going to you have to pick a racer, and are you going to pick the fast hare who's got a great top speed and average speed, but maybe sometimes it's a bit slow and takes a nap? Or do you take the reliable tortoise whose average speed is slower, but he's nice and predictable? So we're going to think about that and how we want our software to be. For non-safety critical systems, the average case performance is often what you're interested in. For your, say, web browser like Google Chrome, you don't care if it takes a few extra seconds once every few days to load, as long as it's fast 99% of the time. And so if you're playing this fictitious game on screen for your web browser, because it's not safety critical, you're going to go with the hare. You're going to go with something where the average case performance is good, and maybe sometimes this worst case performance is bad. But for safety critical systems, the reverse is true. The worst case timing performance is what we're really interested in, not the average case performance. This is because in aerospace, the failure of a safety critical system to meet its timing deadline has quite large negative consequences that you want to avoid. If a pilot wants a plane to pull up and they pull back on the control yoke, they need the system to act upon their input in a predictable and timely manner. If the plane has a 99% chance to respond in under 5 milliseconds, but then once in a while you hit that 1% chance where it takes, say, 10 seconds to respond, then obviously that's a serious problem and you wouldn't want to fly that plane. So let's talk a bit about what worst case execution time actually is. So worst case execution time is the maximum length of time a software component could take to execute in a given environment. On the right here, you can see some C source code with a diagram to the left of it with a control flow graph of that code. The numbers in the little squares there represent how long each part of that code takes to execute. The blue line at the side is showing one possible path through the code. So that path is showing that you take the true branch of both those ifs each time. And if you add up those blocks that it goes through, so 10, 20, 10, 60, 10, you get a total of 110. So maybe you're testing your code here and you take both true branches. And perhaps you're a responsible engineer and you decide, okay, I'm going to get decision coverage as well while I'm doing these timing tests. And so you take the false branch through both of these ifs. And again, you can add up the times and it will come to 85. Great, okay. So we've taken two paths through the code. We've got full decision coverage. Is our timing testing done? Oh no, there is another path through this code that takes a longer amount of time. And that's now shown in the red. So this red path, it goes through the false branch first of the first if, and then it goes through the true branch of the second if. And you see now we're adding up those blocks and it comes to a much longer time. It comes to 140. And so this is, for this very simple diagram here, that's the worst case path through the system. So in the industry, there is no standard way to derive worst case execution time for your software system. However, there are kind of three main approaches which we will see that we're going to talk about now. These three main approaches are static analysis, a dynamic measurement-based approach, and a hybrid static dynamic approach. And we'll talk about each of these in turn now. So the first approach, the static analysis approach. In this approach, you build a model of the target hardware and CPU, and then you feed this model, this software model you've made of the hardware, your assembly code, and then the tool goes off and it combines those two things together to calculate a worst case path through that software based on the model of the CPU and the assembly code. It's not really running anything on the target hardware. It's all done by analyzing the structure and using this model of the CPU. An advantage of this approach is it doesn't require access to your target hardware, and so you free up a physical resource there. It can all be done on some server somewhere else. Disadvantages of this approach is that it tends to produce quite pessimistic results based on how it works, meaning you might not get to fully utilize as much of your target hardware if you depend on worst case estimates from it. And it might also mean that you're not able to meet or satisfy your timing requirements based on this approach. Another problem is it's very much dependent upon the accuracy of the software model of the CPU. When things were simple, when CPUs were relatively simple, it was great. You could do it. But as CPUs have gotten a bit more complex in the kind of the modern era, where you've got multiple layers of cache and memory bus access and cache controllers, branch prediction, superscalar architectures, and out of order execution, and all sorts of clever silicon features like these, it's gotten much harder to build accurate software models of the CPU. It's gotten to the point where this has become very, very difficult to do for modern hardware, but for older hardware, it's still a bit more applicable. Another approach is the dynamic measurement-based approach. As software professionals, we've probably, or even hobbyists, we've probably all done this in some way at some point in our careers. You can put a timer at the start and end of a task and execute it, and you execute tests with your timer in, and you try and stress your system as much as possible. Maybe you run your system tests, maybe you write proper timing tests, and you see how long the task takes to run end to end, and you keep note of that. Advantages of this approach is that it's pretty easy to get started, right? All you need is a timer on your target, or maybe you could use something externally. You could put an oscilloscope on some pins and use that to time things. So really, it doesn't need much to get going with this approach. The other advantage is you're running on the actual hardware. So unlike the static approach, you're not dependent upon some software model of the hardware. The hardware itself is the best model of itself, right? And this is something DO-178C is pretty keen often that you're testing on the real hardware. So there's another advantage there. This approach does have its disadvantages, though. The main problem here is the largest observed execution times you're getting back from your testing aren't necessarily the worst case. You've just executed some tests. How do you know you're observing the worst case and not just maybe a little bit worse than average case? Maybe there's a worse combination of inputs you haven't tried yet. You don't really have a measure of how much confidence you can have in your results. And it's pretty tricky to come up with evidence in this process to support that. In the static approach, you've got a nice clear chain of reasoning. If your model of your CPU is good and your assembly code is correct, then yes, it's going to be a strong argument. But with this dynamic approach, it's much harder to argue that you've done enough testing, and you're not really getting much feedback from the process itself to tell you that you've done enough. So if you do take this kind of approach, one way to mitigate is to use large safety margins. So from the worst case you get back, you add, say, 20, 30%. But obviously now that means you're going to have less utilization of your hardware resources, because you have to account for this extra 20, 30% of time. So this leads me on to talk about a hybrid approach. In this approach, the code is statically analyzed. So your C or Ada or C++ or whatever, that code is statically analyzed to produce a control flow graph. And then you execute your code on target. And as it runs on target, you take measurements from individual blocks of the code. And you feed these block timing measurements back into that static analysis of your software. And then the tool, you have a tool here which goes off and it calculates the worst possible execution time by combining the two things, that static analysis and those real world measurements on target. And here you have the advantage that you're not reliant upon the accuracy of a software model of your hardware. You're running on the actual hardware, so you're inheriting the actual hardware's timing characteristics. And you gain the advantage that the tool can guide you in the filling in of the gaps of your testing, because now you're not dependent upon your own kind of purely on your own kind of human reasoning. The tool is able to assist you because it understands that control flow of the code, and it can apply those measurements such that you can find better worst case paths. It also has the advantage here that now the worst case estimate has clear reasoning behind it. There's a process and an algorithm, and these types of tools also tend to let you add extra data into your analysis, like specifying constraints that might not be necessarily picked up, such as two paths being mutually exclusive or functions behaving differently in different places. So that's the third approach, the hybrid analysis approach. Oh, to mention disadvantages of this approach, we do, so in the dynamic approach, obviously you have the disadvantage that you're still dependent upon having access to the target hardware. So you're collecting measurements from the target hardware, so it needs to be available to do that. And also in this approach, typically to collect the measurements, you might be adding instrumentation into the code. And so this is going to add some overhead onto, say, the code size and execution time, unless you use an instrumentationless approach. But then you need a CPU that supports that kind of stuff with like a branch trace or something. So now we're going to talk about what does DO-178C say about worst case execution time. In true DO-178C non-prescriptive style, it tells you that you need to do timing analysis, but it doesn't tell you how you should do it. If you look through the document, you'll find these various objectives, and we've kind of summarized them in the table here. And so we're going to look through these now together, and we will start with the bottom row there. So the bottom row is taken from table A6 and row 5. So let's have a look at what that says. So table A6, row 5, is talking about executable object code being compatible with the target computer. And under the section heading requirements-based testing methods, you have this activity to perform. So requirements-based hardware and software integration testing, you need to show that it says that typical errors revealed by this method include failure to satisfy execution timing requirements. So this part of DO-178C can be kind of interpreted as saying, collect timing data during requirements-based testing and use worst-case execution time analysis to demonstrate that your software is going to meet its timing deadlines, and of course provide evidence that you have done this with the appropriate traceability. If you are using the static approach we talked about earlier, then you don't actually need to do this. You're probably going to be referring to the section of formal methods, but for all the other approaches, you need to do requirements-based tests for your execution time analysis. Moving on to the next row in that table, we have taken from DO-178C table A5, row 6, which is talking about source code accuracy and consistency. There's the activity 634F, which says the objective is to determine the correctness and consistency of the source code, including ... worst case execution timing. And then it gives you some advice. It says the compiler, including its options, the linker, including its options, and some other features may have impact on the worst case execution timing, and this impact should be assessed. So what this is saying is that you're going to need to analyze your platform and find out in advance the things that are going to affect your worst case execution time and your worst case execution time analysis. And you should look at these and use that information to make sure that you configure your platform and write your software in a way that means you'll actually be able to hopefully meet your timing deadline and be able to carry out your worst case execution time analysis. So these are things you're going to need to analyze and kind of hold through your process. So the examples it gives of things in your platform that can affect things are your code style, platform configuration, and your compiler and linker options. Moving on, the last one in our table here. So in DO-178C table A4, row 13, it says that software partitioning integrity is confirmed. So here, you need to show that your software partitioning mechanism, if you have one, cannot be breached. So you need to make sure and have evidence that your tasks can't overrun any partitioning that you've put in place, such that they can't affect other tasks running. So this is kind of keeping things safe by saying if the worst thing happens and the task overruns, it's not going to affect other tasks. It's all nice and sealed in its own box. So one option you have with this is to use a qualified RTOS. So your qualified RTOS will probably provide assurance that your task can't go over its partition window. The other way you can do this objective is to write tests, and we'll talk about how those tests might look a little bit later. Okay, so now that we've seen those objectives, we actually want to look at what things we can do at what stages of the DO-178C lifecycle to meet those objectives. So we've got the different stages of involvement, the SOI milestones down in the right there, and we'll step through these and see what kind of things we should have ready for these milestones at each one. And we'll have a focus here on starting things early so that they're not a problem later on. So we'll start with, of course, SOI 1, which is your planning phase here. So during the planning, you'll be writing a software verification plan, your SVP, describing how you will achieve the objectives relating to your worst case execution time analysis. So what you can do is you can, and in this document, you're going to include things like you can analyze your platform in advance, and then you can use this analysis to help you throughout your DO-178C lifecycle. You want to identify hardware issues that make timing analysis more complex. For example, maybe your hardware has layers of cache, maybe it has speculative execution or out of order execution, and you're going to want to understand how these are going to affect the timing characteristics and your timing analysis. So testing these early is going to help you in the life cycle. Also, you're going to want to look at your possible choices of compiler and linker options and how they're going to affect timing. For example, compiling at a high optimization level might make things faster in the average case, but maybe it's going to increase the unpredictability of the timing. And so maybe you don't want that extra variation in the timing. At this point, you also want to be looking at what programming features could impact your execution time. So a classic one is passing large structures by value instead of by reference. You want to have a good understanding of those types of things that could affect it. So if you pass a whole structure on the stack in your code, obviously that's going to be slower because it has to copy the whole structure, rather than if you just pass a pointer around. And maybe this is something you want to feed into your coding standard. And also you want to identify language features that are supported by your chosen timing tool. So maybe your timing tool doesn't support C++ template lambda functions or some other trendy thing. And maybe it's best, if you think about it now and get it into your coding standard, that you won't use those things, so that you'll make your life easier when it comes to completing your verification step. And so this analysis, with all the other planning documents, is going to get presented to your certification authority in SOI 1, and so it's good to have done and considered all those things. So during SOI 2, which is the development phase, you're going to be writing your system spec and your high and low level requirements, and these high and low level requirements need to include your timing requirements. During development, it really does pay to begin your timing testing early. So based on those objectives we saw before, here are some more ways you can do that. So analyzing your partition integrity. Even at this point, even at the early stages of development, maybe during system spec, you can still analyze this partitioning integrity, and you can do this with placeholder or dummy code. So if you know what RTOS you're going to use, you can write a task which just has a busy wait loop in it, and you make sure that you know the busy wait is long enough that it's going to exceed the partition boundary that you set. And so what you can do is you can run without the partitioning mechanism in place, or with extra big windows, and check that it does indeed, this busy wait does indeed run for a long time. And then you can put the partitioning mechanism back in place or decrease its size, and then make sure that your busy wait task does indeed get cut off. And this way you can, if you write this into a test that's reusable, then you'll have something that's going to be usable throughout the lifecycle to check that your partitioning integrity is maintained, even if you end up changing platform and RTOS configuration things. You have a test there, and as the project goes on, you can evolve this test and maybe substitute out some of that busy wait for real application code, plus a smaller busy wait to overflow the partition boundary if it wasn't enforced. So that's one thing you can do. Another, you can at this point start writing tests to identify problematic coding constructs and language concurrency features. It does pay again to find these problems early. So for example, I know of a situation where someone was using a language feature to implement mutexes with priority inheritance, and they found quite late in the day that actually this mechanism was way too slow and was causing lots of timing problems, and so they had to roll back to another mechanism. And that cost them a lot of development time, and it did cause problems throughout. So if you'd done an analysis up front, then obviously they could have avoided that, because they'd know there was going to be a timing problem with that concurrency language feature they were using. And thirdly, if you can, and start writing your timing tests for your application early. Fixing worst case issues can sometimes involve large scale changes, maybe even architectural changes. Spotting these as soon as possible is going to save you a lot of time. And so you want to be finding major problems. You don't want to be finding major problems before when you don't want to find major problems as you're starting verification or in verification. You want to find them before that, as they're much cheaper to solve at that stage. Okay, and so in SOI 3, in the verification stage, you can carry on building up those timing tests, those requirements-based timing tests. And then in SOI 4, this is where you're going to be submitting all your final evidence and your evidence and traceability and your full analysis of the worst case execution time. So if we see these activities across the V model here, this is a useful little diagram that is showing when you could potentially start each of these activities. So in red here, we've got that the coding standard constructs are checked that they're supported by the timing tool. We can check that right at the project planning phase. And again, you see with these different ones here, the yellow line where we can check the various options for the linker and the compiler and the RTOS. Again, you can check those right at project planning and use it all the way through the life cycle. And again, in purple, your timing, checking that your code is suitable for timing analysis. This might be checking against your coding standard. You can start that right at the start of implementation. And again, timing tests, writing them, you can start them at the start of implementation. They don't need to be perfect, but getting started with them is hopefully going to reveal issues before they really become a problem. So now we're going to talk a bit about the practicality here. So on target versus on host or on host simulator testing. DO-178C is pretty keen that you do your testing in an environment as close to possible as that which will fly. So if you can test on your real target, do so. If your environment has differences, if your test environment has differences to the real final environment, then you need to have an analysis of those differences, and you need to have a strong argument for why your testing is still valid. However, sometimes it's not practical to start your testing early on target, maybe because you don't have the hardware yet, or there's limited availability of test rigs. So you can still get value out of on-host and on-simulator testing if you start it early, as it's going to let you catch hopefully large timing issues first. You don't necessarily get super accurate numbers from running on a simulator, but it will help reveal architectural and algorithmic timing problems and give you a bit of a ballpark figure. And so there is a bit of a hierarchy here. You can have your, on the actual hardware that will fly as your kind of gold standard, and then maybe a cycle accurate simulator if you can get your hands on it, and then maybe a normal simulator, and finally on host on your Windows PC is kind of the last resort. But maybe you can use all four of these in your workflow, depending on the test. So now we'll talk a bit about manual versus automated testing. So it is possible to do worst case execution time testing manually, but it's only really feasible for very small software projects. We have a graphic here where we have a customer who had been doing their timing testing by hand, and it took them 8-person months each time they had to do it, which is a bit crazy. But with Rapita, they're able to take those 8-person months and get them down to 1-person day. And that just shows the advantage of having a tool to do this kind of stuff for you and help you in the process. So it's really worth considering having an automated process that helps you with your timing analysis. If you do use an automated tool, however, if you're using the output of the tool without checking it, then it needs to be qualified under DO-330, which we'll talk about now. So tool qualification is the process where you provide evidence that a software tool is doing what it's supposed to. As per DO-178C, you need to qualify any software tool that you use that replaces or mitigates any of the DO-178C processes if you're not manually verifying the output of the tool. So this is all described in the DO-330 software tools considerations supplement to DO-178C, and it tells you, that document tells you how to qualify a tool. Often in practice, this is done through, most of the work is done by buying a qualification kit from vendors, although there is always the option to do the work yourself, although often the vendor's already done most of it, so it can pay to just buy one. Okay, so now we're going to talk about what things you should look for in a worst case execution time analysis tool. So some questions. What metrics does it display? Does it display worst case, average, high watermark? What is it going to tell you about your software? If it displays worst case, how realistic are those results produced? Are they overly pessimistic? Are they optimistic? Does it let you configure the analysis to account for extra information? If you're using a hybrid or measurement-based approach, does the tool force you to do instrumentation in a certain way, or is it flexible? Are there people who can support you in integrating the tool? How easy is it to get up and running? Other things to consider are things like instrumentation overhead, if it's using instrumentation, and how easy is it to actually read the results that come out from the tool. And again, other things like display. So does it have support for your continuous integration system that you're using, like Jenkins and Bamboo? And also, does it export results in a format that's suitable to show to your certification authority, or is it all locked behind some proprietary format that you need a viewer to read? And then you also often want to think about licensing. Is the licensing flexible? Is it locked to one person, one project, one location? And also, are there qualification kits available for the tool, or you're going to have to qualify it yourself? So here we're just going to quickly go over a example workflow when using Rapita. So Rapita shows a bunch of metrics. The two important ones for this worst case analysis are the high watermark and the worst case path. So the high watermark is the longest time your task body was observed to run. So here you can see we have a diagram of different runs of the tests. So we have 4 test runs, and run 2 is the longest test run where AF and K all stacked up to be the longest time. And so that's our high watermark run because it was the longest observed run. Whereas worst case is not an observed value, it's an estimate based on combining that static analysis of the code with measurements of the individual blocks of the code. So the Rapita path analysis workflow, essentially what you're going to do is you will input your existing timing tests and use Rapita static analysis and instrumentation of your code to produce a timing report from those measurements of the code. And then you will look at that timing report and you will use the information in there to either increase your high watermark so that it's closer to the estimated worst case, or you will update the analysis, tell it things like mutually exclusive paths to lower the worst case to make it closer to the high watermark. So each time you're closing the difference between the high watermark and the worst case. Here we've just got that process expanded a bit into this diagram here. So first, what you do in RappiTime is you use it to find where the biggest deviation between the high watermark path and the worst case path is. So what's causing the biggest difference? And RappiTime has a contribution time tab that can help you drill down and tell you about that. And so you use that information presented to either improve your testing, and RappiTime will let you do things like view the timing information and your paths in the context of your source code. To do that, it'll help you to figure out where your code went. You can, for example, replay traces, and it can help you understand how to improve your testing such that you can find a worse path through the code and write a test that reveals that. And it will also provide features where you can improve the worst case estimates, so lower it down to make it closer to the high watermark and more accurate. And it provides features like specifying infeasible paths. You can also, if you're still in development, also refactor your code to maybe make the analysis easier as well. And so what you do is you go through this loop. And at each time, at the bottom of the loop, where you're either improving the tests to increase the high watermark or improving the analysis to lower the worst case execution time, each time you do that and go around the loop, finding the biggest discrepancy, you ask yourself, is the cost of the analysis going around the loop again worth the possible risk reduction? And if it is, you go around again and you find the next biggest discrepancy. And hopefully by the end of it, by looping through this process, you're going to develop a really good set of timing tests with good, strong documentation behind them as you document as you go. Of course, it's very important with RappiTime being a hybrid tool that you have good coverage of your code. You ideally want to be executing every block, and RappiTime provides views to help you see that. You also want to make sure that you're executing loops so they iterate the maximum number of times. Or you can manually configure that if you need to, if you can't write tests to do that. And you want to make sure that you're documenting as you go. So document the environment that you're running the tests in, any optimizations you apply to your code, and any additional test cases created and why, and what paths led you to create those. Once you've done all that documentation and gone around that workflow, hopefully you'll end up with a great set of really strong timing tests, a final high watermark measurement that is an observed value which you can submit to your certification authorities with a really strong reasoning behind it based on that path analysis that you did for why it's the observed worst case. And you can also include the estimated worst case from the tool and an analysis of the difference between those, and you can report that and have maybe a discussion in your document of any engineering margin and residual risks. So that's a really quick whistle-top tour through that process. So I believe next we have a demo video which I recorded, which shows this workflow in practice. So I believe I will hand over to Nick to start that video. In this demo, I will demonstrate the RappiTime recommended workflow. The target board is an STM32F4 Discovery, which has an ARM Cortex-M4 processor, an LCD screen, and a 3-axis gyroscope. The application running on the board uses the LCD screen and gyroscope to display a virtual horizon that tilts on the screen when you tilt the board. If you tilt too hard to the left or to the right, the application gives a bank angle warning. If you tilt too hard down, then a pull-up warning is given. The application uses a real-time operating system called FreeRTOS. It has 8 tasks running that manage things like the LCD display, checking the buttons, and checking the sensors. The compiler used is GCC and is invoked through a makefile build system. I'll be collecting timing data through the board's GPIO pins using our timing data logger, the RTBX. RappiTime automatically instruments the code so that as it runs, ID numbers are written to the GPIO pins. These IDs correspond to positions in the code. The RTBX reads the ID numbers in real time, assigns a timestamp, then compresses and stores the data on the fly. Here is the RVS Project Manager. It's the entry point for all the RVS tools. All the workflow actions you see me do in here can also be run on the command line. In this drop-down, I can see the various integrations I've set up in this project. I'm going to select my timing test integration that uses the RTBX. Down the right side here, you can see the steps that need to be completed in order to produce my timing report. If I click Prepare, RVS will start analyzing the code in order to build a database of its structure. This is the static analysis step of RVS. Now that RVS has done its static analysis of the code, I can run some tests and gather some timing measurements. I will be driving my timing test today using Rapitest, though it's worth noting that RappiTime can be used standalone with any test framework. Rapitest supports various ways of writing tests, one of which is spreadsheets. Here you can see a spreadsheet containing a simple test for the application. My unit under test is the function runLCDTask. This is the task body that is used to draw the virtual horizon to the screen. Here I define some test variables, and in the support section I declare extra functions I want to call in my test. The table here contains the test actions and the test vectors. Each row represents an action to perform in the test, such as set or check. The columns represent data to use with that action, so they are the test vectors. Here are a couple of for loops used in the test. When running the first for loop, this test vector will gradually increase the roll sensor value, causing the horizon to bank to the right. Here the test checks that no warning message is displayed while the roll value is in the safe range. Next, the test continues to bank to the right into the unsafe range and checks that a warning is given. The other test vectors run those same test actions, but for banking to the left and pitching up and down. Let's now run this test. I click the Build dialog and select my test to run. RVS converts the spreadsheet into the project's native language, in this case C. It then executes the make build command again, using the wrapper to transparently substitute in an instrumented version of each of the application source files. It also compiles in the generated test code and test framework. The instrumented executable is now being loaded onto the target. We see the test exercising the software, causing the horizon to roll and pitch up and down. As this test is running, timing data is being gathered on the RTBX. Here is the RTBX web interface. You can see the timing data being collected from the GPIO pins. The RTBX can be controlled from this web interface, or as in this project, via the command line. When the data has been processed, the report will automatically open. Here is the combined Rapitest and RappiTime report. We can see from this table that all our functional tests passed. However, today we are most interested in timing results. The execution time tab shows 5 different metrics for each function. Yellow is the minimum time recorded. Green is the average time recorded. Purple is the high watermark time. That is, how long a function took to run on the longest run of the route. The route in this case being the task body of the LCD task. Red is the maximum time observed for a function across all runs of route. Note that the high watermark and the maximum metric show different things. High watermark gives timings for blocks of functions during the longest run of the route function, whereas the maximum for a function or block includes all measurements made, not just measurements from the longest run of route. Blue is the worst case execution time estimate for each function. This is not an observed quantity. Instead, the maximum measured time for each individual code block within each function is combined with a static analysis of the code's control flow to estimate a worst case path and a worst case execution time for the task. Notice that the worst case in blue, calculated by RappiTime, is much larger than the longest run achieved by our testing, shown in the purple high watermark value. This lets me know that I need to improve my testing or account for something in my analysis. When performing timing analysis, it is important that you have a good exploration of the possible paths through the code. Rapitime provides a code coverage view to help with this, showing which blocks and calls have been tested. Rapitime also lets you see the maximum number of observed times each loop has been iterated around on the execution time tab. This max observed iteration count is used in the worst case estimate. You can add supplemental data to the measurements by configuring a loop's max possible iterations count manually. This extra data will be included in the worst case estimate. Considering the testing and analysis of loop bounds is important, as loops often have a high impact on a system's execution times. This is the contribution time tab. It shows how much the code blocks within a function contribute to the overall metrics, excluding any sub-function calls. This contribution tab is useful for guiding optimization effort, as I can see which functions are contributing the most to metrics, whether it be average, high watermark, or worst case. If I expand the differences column and sort by worst case minus high watermark, I can confirm that the display alert function contains the largest discrepancy between the high watermark and worst case. This means it is an excellent candidate to consider when improving the timing testing, which we noted was required on the execution time tab. If I drill down into the display alert function, I can see how the individual blocks of code in that function contribute to the various metrics. Bringing up the Properties window lets me see a quick preview of the code associated with particular blocks. Notice the code block for I.13 has a large worst case time, but is not on the high watermark path. I.13, we can see, is associated with the code that displays the pull-up alert on the LCD screen. Clicking the Source Code button lets me see the timing metric paths highlighted on the code. I can choose to show blocks tested, worst case path, and high watermark path all overlaid on the code. Rapitime is showing me that the high watermark path, our best timing test, goes through the path to display the bank angle alert, but the pull-up alert is not executed on that run of the task. The worst case path estimate lets me see that if I were to write a test to trigger both bank angle and the pull-up warning, I should have a substantial gain in the amount of time my longest task run takes to execute. Rapitime has let me quickly home in on where to spend my timing analysis effort. So now let's improve the testing of our timing requirements. Let's reopen the spreadsheet test we ran before. Make a new test that exercises both roll and pitch at the same time. I'll copy the existing bank angle test vectors. Next, I'll rename them to indicate they test both roll and pitch. Since I already have tests that check the display of the alert messages, I'll set the warn value to 0 so the first for loop doesn't execute. Next, I'll set the checks for the bank and pitch warnings to a colon to indicate I don't care about checking the output. Since the test vectors I copied already are increasing the magnitude of the roll, all I need to do is set the pitch to the iterator I to cause the pitch to change at the same time as the roll. As both values increase, this should cause them to trigger the alert message to display on screen for both the roll and the pitch, and so drive the execution down the worst case path. And finally, I'll blank out the last warning check here, as I'm purely interested in testing for timing. Now that we've updated the tests, let's run them again. I select Build and ensure the Run and Report stages are ticked. RVS will now compile in my new test and collect timing results as the tests run. Watching the LCD screen, we can see the old tests are blanking to the left and to the right and pitching up and down, running. And now the new timing tests we added are also run. We can see these altering the magnitude of the roll and the pitch at the same time, which should now execute Rapitime's estimated worst case path and give us some better real-world timing measurements. Now the data has processed, we can see a new timing report. On the execution time tab, we see the same worst case execution time estimate, but we now have a larger high watermark time. This is good, as it means we have a better timing test for our software. If we switch to the contribution time tab for display alerts, we can see in the chart the high watermark and the worst case bars are now almost even. If we expand the difference column, I can see that there is now only a 90 microsecond difference between worst case and high watermark. On the Invocations tab, I can clearly see from the shape of the graph with the two stepped up regions at the end that the test did what we expected it to do timing-wise. And here you can see the new high watermark run of the task. Switching back to the source code view, the purple highlighting is showing us that both the bank angle and pull-up alert were taken by the high watermark path, and so I've successfully improved the timing testing. In some cases, when you look at the code in a tool, you'll find that the suggested worst-case paths are not possible. For example, conditional code blocks might be mutually exclusive, or maybe certain paths only happen a limited number of times around a loop. In this case, RappiTime provides a rich language for expressing these constraints, which will be reflected in the worst-case path estimate and included in the reports. For example, if I scroll down here, you'll see that this if true branch is not included on the worst-case path. This is because I added a constraint saying that if bank angle and pull-up alerts are both executed, then this if true block cannot also be executed. I told the tool about this mutual exclusion and it factored it into its worst-case path estimate. In conclusion, we have used RappiTime to perform worst-case path analysis in an on-target environment. We have taken existing functional tests, combined them with RappiTime's automatic instrumentation to collect real-world timing measurements down to the statement block level. We have talked about the importance of path exploration for giving us confidence in the analysis, and have seen how RappiTime's coverage tab and loop iteration display can help us with this. We have used RappiTime's execution tab to view our overall timing values, and then used the contribution time tab to find the best place to apply our timing analysis effort. Finally, we have seen how repeating the process of finding the next biggest discrepancy between the worst case and the high watermark, and then dealing with it by either improving the testing to make the high watermark higher, or improving the analysis to make the worst case lower, helps us develop good, repeatable, worst case timing tests.
Thank you, Matt, for those slides and that fascinating demo. A bit longer than our usual demos, but I think it was very interesting. So thank you for that. Okay, now we're moving on to Rolls-Royce part of the presentation. So I'm going to pass over to Dr. Stephen Law, who's Senior Principal Software Engineer at Rolls-Royce.
Thank you, Nick. So yeah, without further ado, I'm going to just step through a couple of slides that talk about how we perform worst case execution time at Rolls-Royce and what it means to the systems that we're developing here. So we develop DAL-A, C and E software systems to control and monitor our Rolls-Royce power systems. That predominantly means aircraft engines, largely in the civil aerospace business. We've had a close working relationship with Rapita now for 10 years. It's a relationship that we are maturing now as we start to use more RVS tools. And finally, a key point to our worst case execution time story is to point out that we design and deploy our own in-house processors. We're currently on the 6th iteration of that. The two pictures I'm showing on the screen here, the picture on the left is our next generation UltraFan aircraft engine, which contains a software system of around 10 processors in the order of approaching the order of 1 million lines of code. On the right hand side is one of the electronic control systems, engine electronic control systems that we use to control our jet engines. Obviously the two pictures are not to scale. So why do we do worst case execution time analysis? I'm repeating a bit here some of the material that Matt said earlier. You know, what does DO-178 prescribe? The key point I want to pull out of it, because it significantly impacts how we perform our analysis, is that you must ensure that you take account of compiler, linker and hardware features that could implement or that could impact the worst case execution time. you must assess that impact. That has a significant impact on how we then perform our analysis, which I'm going to give you a quick slide on later. So what do we use our worst case execution time results for? What do they actually mean to us? Why do we need to analyze them? Well, essentially, when we receive our worst case execution time results from Rapita, we then input them into a schedulability analysis process. We use that process to confirm compliance to high-level timing requirements. What kind of requirements are these? Well, they could be requirements that, for instance, at the engine level state that we would sense and respond to a significant engine event within a set amount of time. For instance, if we detected that there was an engine fire, we need to shut down the engine within a prescribed amount of time. And that's the kind of requirements that are passed down to us from our airframers and from, to a lesser extent, certification authorities. These requirements then feed into lower level software requirements that include restrictions such as iteration rates. We need to repeat reading a sensor every so often. Delays. If we move an actuator, we need to wait a set period of time before confirming that that actuator has indeed moved to a correct position. And finally, response times. In the worst case, when everything is happening at the same time, what is the longest possible response time for task A or task B across our system? And I'd argue, given that I've studied this for the last 10 years now, that from a technical point of view, worst case execution time analysis is arguably one of the hardest software analyses to perform. I put arguably on that, and I'm happy to discuss. What's our worst case execution time analysis journey? What's the history for us? So previous iterations of our processor used an in-house static analysis worst case execution time tool. The key point is that that tool was supported by a timing accurate simulator. When we moved to the 6th iteration of our processor several years ago now, it was deemed that it was effectively no longer feasible to produce a timing accurate simulator for the new processor. We introduced some more complex processor features that we felt meant that we could no longer accurately simulate the processor's behavior. We also suffered a lot of issues that the expertise of maintaining such tooling was in short supply. So our approach was effectively to talk to Rapita, and we worked with them from the very early days of the design of our processor to ensure that we could integrate Rapita with the processor and roll it out alongside the new processor to project. To date, we've now certified 3 DALE aircraft engine control systems using Rapita, each one in the order of several 100,000 lines of code. We're now in the process of rolling out a new software architecture and looking to our next generation aircraft engine control systems. As part of that journey, we're moving over to a model-based software development approach, which is supported by RapidTest, RapidCover, RapidCover 0 and RapidTime 0. So we're now taking on a large number of the wider RVS suite. Crucially, one thing I'm quite keen about, and one thing I'm quite excited about, is that rolling out RapidTime 0 versus RapidTime has allowed us to remove all timing instrumentation from our process, therefore removing all the overheads that come with that. That has been a significant boost for us. So finally then, I just wanted to talk around our tooling infrastructure and the actual details of how we perform worst case execution time analysis for our control systems. As I said, we're talking systems of the order of 500,000 to 1 million lines of code, substantial systems that have a large number of tests alongside them. We feed we essentially have a system that's controlled by our continuous integration system, Azure DevOps, that is integrated with Rapita and a number of cards that interface directly to Rapita trace boxes. So essentially, all the code that test card executes is measured using a Rapita trace box. Those traces are passed out to Rapitime for worst case execution time analysis, and that gives us a system level worst case execution time result. We finally feed that into our schedulability analysis process. That final step is performed offline and outside of our CI system. We feed our CI system at the start with a number of different levels of testing. Firstly, we use free running builds. Simply, we download the build to the processor and we allow it to just run. The next step is we use our software integration tests. And the final step, in order to fill any of the final gaps, we use our component tests. Our component tests are developed both using Rapitest for manually coded components, and for model-based developed components, we use Simulink test. Both have been integrated with Rapitime. So that was just, from my point of view, a very quick run through of how we perform timing analysis at Rolls-Royce, what it means to us, and I'm going to pass back to Nick.
First up for Rapita, a question from Peter. So this is for you, Matthew. How is any variation of processor performance, and therefore WCET, due to external factors such as ambient temperature, heat, accounted for? How's that accounted for in the WCET analysis?
Excellent question. It's rather challenging, but there are a couple of things that you could do. The first is if you can run some tests to understand right at the start of your project, when you know you've got your hardware platform, understand how increases in temperature are going to affect that. So you could maybe write some tests, and obviously you're going to need to measure the temperature if you can of that system, and you can characterize how heat affects it. And then the other way you can do that is if you've got all your timing tests already built, or if you've got any, I guess, you can make sure you also run those in different environments, so at different temperatures. Maybe if it just heats up itself, you can just leave it running over and over the same tests and make sure you're collecting that data, and just tag that data with the temperature. But excellent, it's like a really difficult problem to deal with, but a testing based approach is probably your best bet here, because it is so finicky and with the real world.
Absolutely. Not something you could test very easily on a simulator, I would imagine. Great. So next up, I've got one for you, Stephen. I think it's a Rolls-Royce related one. Yeah. So what is Rolls-Royce processor architecture? I think you mentioned that you make your own, or you have your own designs. And why do you design your own processor?
So our processor is a single core execution time invariant device, so we ensure that the execution time of the device is deterministic. And one of the reasons that we develop our own processor is to make this process easier. It does make our worst case execution time analysis arguments easier, but it also gives us control over our supply chain. We have very long project timescales. We have and need to support projects for multiple decades, and in order to support those, we need to have complete control over our supply chain for the entire length that product is out in the market, as well as the long development lead times that we have ahead of it. So there's a few reasons.
So it's commercial and technical at the same time.
That's right. That's right.
Yeah.
It makes our certification work easier, and it controls our supply chain.
Excellent. Thank you very much, Stephen. That makes a lot of sense. Okay, next up, another for you, Matt. How to predict how many GPIO pins? I think that might be after, but it's not there. How many GPIO pins are needed for a measure? Does it depend on the complexity of the code under test?
Okay, good question. The first thing to say would be you don't need to output your data necessarily through GPIO pins with Rapitime. You can use a variety of mechanisms. You're not locked down. You can, basically anything you can imagine you can use, just as long as it's got enough bandwidth. So Ethernet, GPIO, debuggers, all sorts. But if you were using GPIO pins, then for our typical integration with our kind of standard configuration, Rapitime will insert a unique iPoint ID at the start and the end of every function, and then in the middle it just reuses iPoint IDs. If you have, say, 5 GPIO pins available, then you can have 2 to the power of 5 divided by 2 number of functions. So it's basically, if you want to know how many GPIO pins you need, work out how many functions you have, and then put it to the power of 2 to the power of the number of functions minus 1, and then you can calculate it. There is facility in Rapitime if you kind of stray from the standard workflow to do a bit more of a complex ID packing, where you can actually get away with even fewer GPIO pins, but it's requires a little more integration effort. So by standard, 2 to the power of n minus 1.
Far too much maths for me, but I'm sure that makes sense to some of you. Thank you.
Sorry. Sorry, n is the number of GPIO pins there. Sorry, you can support 2 to the power of n, where n is the number of GPIO pins. Yeah.
Okay, lovely. Thank you.
Yeah.
While I've got you here, Matt, I've got another one for you. May I use Rapitime without using RVS to generate tests?
Yes, definitely. So in my example, I used Rapitest, but you can use whatever you like. Rapitime can be used standalone with whatever test framework you have.
Cool. That's a nice, simple answer. Okay, back to you for one, please, Stephen. This is from Sarah. What special things do you have to do? Sorry, I'm just trying to interpret this a little bit. What special things do the Rolls-Royce testing team have to do to your existing tests to achieve coverage?
Sure. So actually, we don't do additional timing testing beyond our formal testing. We are in some of our previous projects, we've simply used the formal tests that we need to produce anyway to prove the functionality of our software or to show compliance to our requirements. Moving forwards, we are following a process of much more developer-driven test development, further ahead of the formal testing that will then occur later. We can use both for our timing analysis. That provides us with enough coverage according to our process and qualified tooling.
Excellent, thank you. And finally, I'm conscious we're about to hit the 15 mark. That's 15 minutes past the hour, and I don't like to go any further than that. So let's finish off with one more question for Matt. This is from Laurent, and it is, what is the footprint for the instrumentation? Assuming that the whole code with instrumentation will no more fit in the target memory, is there automation at the side of Rapitime to prepare and deploy automatically the binary code for each software part analyzed step by step?
Okay. So there's, I guess, two questions there. The first is, what is the footprint of Rapitime? So if you're using Rapitime 0, which has no instrumentation, then there is no footprint. You can just get it all from the CPU branch trace. If you are using Rapitime with instrumentation, then I'm afraid it really does depend on your target hardware and what resources you have available. The iPoint instructions themselves can be customized to take advantage of what your target has available, but it does really depend on the target hardware and the code structure. In terms of situations where you can't fit all the instrumentation into one build. Like, you can't instrument everything all at once. RapiTime has features that let you turn on certain parts of the cool tree for instrumentation. So actually in our documentation of a recommended workflow, we kind of talk a bit about that, where you can only do an instrument a partial path at once. And so we have a time bands feature, which kind of lets you take levels down particular parts of the cool tree. So yes, there is kind of automated facility to help you with that, where it will only instrument certain parts of the code if you tell it what your route is.